Hello class, my group and I were assigned chapter 15, which was population and the environment. In my group, we had Adam Strisbert, myself, David Hauswander, Sam Barnett, Liam Fraser, and Willem van der Ecker. To start us off with chapter 15, section 1, the dynamics of population growth, we start off with human growth has been consistently slow for ages. Only within the past 200 years has rapid global population growth become a reality at an unprecedented, alarming speed. It is slowing down, but it is still going up. Around 1800, the population was equivalent to 1 billion people worldwide. In 1950, the population was equivalent to 2.5 billion people. This number shot up in only 150 years by 1.5 billion. This is pretty crazy. After World War II, baby boom period, it doubled. People were coming home from the war, many soldiers were killed, the population needed to be fixed. People got down to work and got busy. Around the year 2000, the population was a whopping 6 billion. By 2010, just a decade after, the population was equivalent to 7 billion and still on the rise today. In our first graph over here, we have graph figure 15.1, which shows from 1750 to 2100, the vertical axis, which shows billions, and the horizontal axis, which shows our year, in more developed and less developed countries. In this graph, we can see that the population has been growing and growing fast, especially in less developed countries. And projected by the year 2090, we will be well over 10 billion people worldwide. Growing rate. Our growth rate of 2% every year does not seem huge, but I assure you it is. It adds up incredibly quick, and a population of 5 billion that continue to grow at just a mere 2% per year, for example, would reach 20 billion in 7 years and around 40 billion in little over a century. This is very crazy, and that's way too many mouths to feed in this world at our current rate. Some key terms in this section. Exponential growth, a value that increases by the same percentage in each time period, such as population increasing by the same percentage every year. Neo-Malthusian is a perspective, the modern version of Thomas Malthus' argument that human population growth can lead to catastrophic and ecological consequences and an increase in the human death rate. We saw this as a prime example in the hurricanes that hit Florida not too long ago. Population growth is the rate, the annual change in population of a given area expressed as a percentage. Gross annual population is the increase, the total numerical increase in population for a given region over a specific year. In this table, which is table 15.1, we can see the global population growth rate and average gross annual increase. To start us off here, we can see the population growth rate in percentages, which in 1950s started at 1.8, 1960s jumped up to 2%, 1970s went down a little bit by a tenth, down to 1.9, 80s we dropped again down to 1.8, dropped another tenth. In the 1990s, we saw a steeper decline to 1.4. In the 2000s, we hit 1.23, still going down, but still very high. And in the 2010s, we have 1.18, which is still going down, but still very high. The average annual increase in millions is our next part of this graph. Table, I should say. And in the 1950s, it was 50.6 in millions. In the 1960s, specific time right after the baby boom, we grew by 15.1%, so we're at 65.7. In the 1970s, we jumped again to 75.6. The 80s, we jumped to 85.3. 90s, we saw a slight decline to 81.6. In the 2000s, we saw another decline to 76.5. And in the 2010s, we saw a pretty sharp increase to 84.1. Two graphs for you here. Figure 15.2 in your book shows the net annual increase in population by decade from 1750 to 2100. On our vertical axis here, we have millions that start at 0 and go up to 100. On our horizontal, we start with the year 1750 and go up by every 20 years to 2090. We also can see more developed countries and less developed countries. And in this specific graph, we see a very steady increase from 1750 to around 1890. And then once the year 1910 hits, we see it increase. And specifically at 1950, after World War II, we see a monster increase to around almost 90 million. In our second graph here, 15.3, which shows the world population growth rate from 1950 to 2010 with projections to 2100. On our vertical axis here, we have population growth rate in percentage per year, and we have 0 to 2.5. And then on our horizontal axis, we have our year from 1955 to 2095. We can see on our vertical axis that we start at right around 1.75, but then we have a little increase and it just gets above 2%. And then after that, in the year around 1985, we drop, and then ever since 1985, we have been steadily decreasing.
So this is chapter 15.2, predicting future population growth. I'm just going to go through the key terms to start here. First, we have population momentum. Population momentum is the tendency for a population to continue to grow, even if the fertility rate falls to a replacement level, as long as a high proportion of the population is in young age cohorts. Second, population age, a profile and estimate of the number of people within given age groups in a country at a point in time. Third, we have fertility rates, the average number of live births per woman in a society. Fourth, we have replacement fertility level, the fertility level that will result in a stable population. The fifth, we have population cohort. It's just the group of people born within a specific period in a country. So, as we could talk about, there's a lot of variance in predicting future population growth. This all depends on development in countries, and we'll get more into that later on in this presentation, but it's very dependent on fertility rates and the future, and which can be hard to estimate, as not all women are going to have the same amount of kids in their life. So I'll get into that more. Right here, we have figure 15.5. This is just a figure that shows the estimated population in the world up to 2100. The middle cohort here uses the estimated fertility rate across the world. The high variant is 0.5 births above the estimate, and the low estimate is 0.5 births below the estimate. So as we can see here, this graph varies quite a lot as we can go from the predicted fertility rate, and we'll grow to about 11 million people in 2100, versus in the high variant, we could grow to up to 16 million people. Whereas in some lower instances, if we have lower fertility rate, we could actually fall and have our population drop down to about 7.5-ish million people. Next, we're going to talk about population momentum. Remember, population momentum is the tendency for population to continue to grow even if the fertility rate falls to the replacement level, as long as the population is young age cohorts. So fertility rates have a huge effect on populations, obviously. I mean, the more kids you're going to have, the more your population is going to grow. So fertility can be affected by lots of things, education being number one, family planning. As we can see, countries with more education tend to have lower birth rates, just based on women having better education and higher paying jobs, more work to do. Then in more developing countries, we see lot higher birth rates and fertility rates. In sub-Saharan African countries, we even see 5+ per women. In many instances, this is very, very bad, and it's very not sustainable, as I'll get into. In figure 15.6 here, we can see in a country, and we can talk about our total population. We start off with our population over 50 using 1 million. We use an average birth rate, and our population will grow each year exponentially. But as we can see throughout our 25-year increments, we grow and grow and grow, and this is not really a sustainable option for our country. And it can get very hard because most countries don't develop at the same rate as many others, and it can be very tough on everyone. The lasting effects of population growth. Um, so as I talked about earlier, sub-Saharan Africa has very large differences in mortality rates, fertility rates. So we can see that pyramid shape coming out of the graph here in figure 15.7. As well, along with the fact that death rates are not as high, which will drive up our pyramid here, which makes it a lot more easy to see. The most interesting one here to see is China. So China actually restricted the amount of babies they could have in their country at a certain time period here, so we can see where their age cohort sinks, and we can see the 20-year increments where the cohorts are larger because there were no restrictions on having children. And then over in Western Europe, we see a pretty normal type graph here. So one is similar we would see in the United States, a large baby boomer population and a much smaller growing, much more sustainable replacement level population toward younger age cohorts.
So the next part of the chapter is the theory of demographic transition. The definition I want you to remember for that is demographic transition, the tendency for first death rates and then birth rates to fall as a society develops economically, population growth rates first increase and eventually decrease. So we show this in a graph. So we first have the first scenario. This is pre-industrial revolution, which is right here. It's stable. We still have high birth rate, high death rate. Nothing is very developed. There is not a good healthcare system, not a good education system. A lot of people are still going from place to place. There's not good standards. Anyway, scenario 3, this is middle of the industrial revolution. Death rates fall. People's living conditions get better. Healthcare gets better. A lot of things get better. But birth stays high because people still see the value of having a large family because kids can still work. Then we have another scenario where this is still kind of more post-industrial revolution where people start getting educated. This is where we see birth rates fall. This is mainly because families or I guess parents don't see the positives in having kids anymore. The negative outweigh the positives, so kids are not as interesting anymore. See birth rates plummet. Scenario 4 is where both birth and death rates are low, meaning that's stable. This is pretty much what we live in today. We see this in Japan, South Korea, the US, and Western Europe. And then we have scenario 5, where that it's not on the graph, but something we as a group came up with, which is very true today, is that we see that birth rates are plummeting below death rates, meaning that there's more death than there's birth. And this is mainly in, as we see, South Korea, Japan, the US, Canada, and Western Europe. And this is probably what's going to happen in the future in these countries unless there's more change to come. Then we have the investment and family planning. So the population pyramid on the left shows when there is investment in education and family planning. We see that very young, there's going to be less young people, more middle-aged people, and then older people as well. If there's no investment in education and family planning, we see a lot of young people, and it gradually becomes less because there's no education, people won't see as much value in having less kids than more kids. The last part is the correlation between fertility rate and GDP per capita. So this graph shows that if you have a lower GDP per capita, the fertility rate goes up. And if you have a higher fertility rate, your GDP is lower. And so the same is with fertility rate. If it's a lot lower, your GDP per capita is going to be higher. If it's going to be higher, fertility rate is going to be lower.
Welcome to today's presentation on economic growth and population. Over the next few slides, we're going to go over some of the key concepts and impacts of this chapter. We will explore the complex interplay between economic growth, population dynamics, and the sustainable use of natural resources. We'll look at how production functions drive economic output, how population changes can impact these dynamics, and the vital role resources play in shaping long-term growth. By understanding these relationships, we can better address the challenges and opportunities that lay ahead for global development. Today, we'll be covering several key economic concepts that shape production and market behavior. First, we'll discuss constant returns to scale, where output increases proportionally with input. Then we'll explore the law of diminishing returns, which shows how additional input eventually leads to smaller increases in output. Capital shallowing will highlight the effects of insufficient capital accumulation. We'll also dive into technological progress, which drives productivity improvements. Next, we'll examine economies of scale, where larger production scales lead to lower costs. And finish by addressing market failure, when markets fail to efficiently allocate resources. A few more definitions that we have in this section of the chapter are per capita output, which measures the average output per person in an economy. We'll also cover capital formation, the process of building up a nation's capital goods. Then we'll look at natural resource limitations, highlighting how finite resources can impact economic sustainability. Next, we'll discuss natural capital, which refers to the world's stock of natural resources and ecosystems. We'll also touch on externalities, which are the unintended side effects of economic activity. Finally, we'll explore income inequality, which measures the unequal distribution of income across society. In this chapter, we'll also be discussing utility functions such as the Cobb-Douglas function, which are central to understanding consumer satisfaction in economic models. The Cobb-Douglas function that we're looking at, the utility of X and Y, represents how a consumer derives utility from two goods, X and Y. The exponents A and 1 minus A reflect the consumer's preferences for each good, showing how much satisfaction they gain from consuming each. Outputs in this model depend both on the scaling factor A and these preferences, which guide how resources are allocated in an economy. Understanding this function helps us analyze decisions around resource distribution and overall economic welfare. When further examining the Cobb-Douglas production function, where capital Q represents output, capital A with the lowercase t is technological progress, capital K is labor, or capital K is capital, and capital L is labor. The exponents A, lowercase a and b reflect the contributions of capital and labor to production, with the key condition that A plus B is equal to 1, which ensures constant returns to scale. This means that if we increase both capital and labor by the same proportion, output will increase by that proportion as well. However, when we increase only one input, like labor, we will face diminishing returns as each additional unit of labor results in smaller increases in output. Under the natural capital utility function, we've expanded the Cobb-Douglas production function to include N, which is natural capital. By introducing natural capital, we highlight the importance of resources like land, water, and minerals in the production process. The extension of the model allows us to better address real-world constraints such as resource depletion and shows how limitations in natural capital can directly affect output. Here, dependency ratios, which measure the proportion of dependents to the working age population, often shifting economic burdens as the populations age or grow rapidly. This leads to income inequality, as rapid population growth can suppress wages, multiplying inequality within societies. Lastly, natural resource limitations play a crucial role, especially in developing nations, where resource scarcity intensifies economic struggles. Together, these factors create complex challenges that impact sustainable growth and prosperity. When discussing externalities, which are unintended side effects of economic activities that affect third parties, a common example is pollution, such as the emissions from factories that contaminate air and water, or deforestation, where logging operations destroy ecosystems and reduce biodiversity. These externalities occur because the full costs are not reflected in the market prices, meaning businesses or individuals don't bear the true environmental cost of their actions. We'll also discuss open access resources like fisheries or forests, where overuse happens because no one owns or manages the resource. For example, in many coastal regions, overfishing depletes fishing stocks faster than they can regenerate, affecting local economies and food security. Similarly, deforestation, particularly in tropical rainforests, continues largely unchecked, contributing to habitat loss and climate change. An example of this is the desertification in the Sahel region, a region in Africa where poor land management and climate change have led to the expansion of desert areas, diminishing agricultural productivity and displacing communities. In urban centers, we see the growth of slums, where overcrowding and a lack of infrastructure create poor living conditions, and the environment suffers from unmanaged waste and air pollution. These examples show how unregulated markets can fail to address the depletion of resources or pollution, resulting in long-term economic and social consequences. The concept of demographic transition, particularly the demographic gift that occurs during periods of low dependency, when a country has a larger working age population compared to dependents. This shift presents a unique opportunity for economic growth, as fewer resources are needed to support dependents and more can be directed toward productive investments. Countries like South Korea and Singapore have leveraged this demographic window by implementing sound policies such as investing in education, infrastructure, and technological innovation. These efforts have allowed them to capitalize on their growing, productive populations and achieve rapid economic development. In summary, we've explored several key concepts: natural capital, the law of diminishing returns, and dependency ratios, all of which play crucial roles in shaping economic growth and development. We've seen how population dynamics can both drive growth and create constraints, especially when resources are limited or population pressures increase. To address these challenges, it's clear that integrating population and resource considerations into growth models is essential. Sustainable policies and technological progress are critical in ensuring that we can harness the full potential of our populations while managing resources effectively. In conclusion, the sound economic policies and careful resource management are key to overcoming population-related economic challenges.
All right. For 15.5, ecological perspective on population growth, we have our three key terms, which are carrying capacity, solar flux, and identity. Some carrying capacity examples. Ecological approach is based on carrying capacity. This implies that there are practical limitations to the population that can occupy a specific region.
As an example, we can think of a herd of grazing animals exceeding the land's carrying capacity. Food will run short, many individuals will starve, and the population will decrease naturally to a more sustainable level. This is the same process for plant life as well. All life on Earth depends on the ability of plants to capture solar energy. The available solar flux or flow of sunlight to Earth's surface is thus the ultimate determining factor of carrying capacity. An example of an area with poor carrying capacity due to low solar flux would be the polar regions, specifically areas like Antarctica or parts of the Arctic tundra. In contrast, tropical rainforests near the equator receive much higher solar flux, leading to high primary productivity and a much higher carrying capacity for diverse species. Fossil fuels have historically been the leader in energy production. Fossil fuels have provided far more power for industrialization than any solar flux captured either directly through solar energy systems or indirectly through hydroelectric and wind power. A prime example would be the current global climate change caused by the burning of fossil fuels. Fossil fuels consumption leads to negative environmental effects such as air pollution, greenhouse gas emissions, acid rain, water contamination, habitat destruction. A quantifiable example would be the erosion and degradation of topsoil. Topsoil losses worldwide are currently estimated at 24 billion tons annually, with nearly 11% of the world's vegetated lands suffering moderate to extreme degradation, as well as the loss of biodiversity, which currently sees more species driven extinct every year than at any time in the preceding 65 million years. So how can we quantify these impacts? We can conceptualize the interrelationship of population, economic growth, and environment in an equation linking all three, which is known as IPAT. This equation is an identity. The right side of the equation can be read as the following: population times output divided by population times the ecological impact divided by output. IPAT gives little insight to the specifics behind these very broad concepts. IPAT often receives criticism because it assumes that the P, the A, and the T are all independent of one another, when in fact they are directly correlated. This equation is known as an identity, a mathematical statement that is true by definition. (15.6) Population and policies for the 21st century. Most analysts accept that increasing the population places extra stress on the environment and resources and agree that slower population growth in the future is essential. So how can we accomplish this? The most prominent example of this is China's draconian one-child policy. Such policies have been discredited both on human rights accounts and because they fail to alter basic initiatives regarding fertility. Rather than changing people's desires to have children, this policy often increases the use of forced abortions and increased sterilization of women. Some of the results from this policy are the following. The men outnumbered women by at least 33 million, according to a 2010 consensus. Projected surplus of 40 to 50 million bachelors in China at the mid-century mark. Estimated 13 million children in China have not been registered, which leads to them not having access to proper healthcare or even an education. It is also estimated that between 1970 and 2010, more than 125 million women have been missing through abortion or neglect, resulting in death. So alternate approaches. How can we lower birth rates? It is not necessary to apply coercive policies with the perverse effects they had on human rights such as China. The experience of several countries such as Iran shows that birth rates can decrease when people, especially women, reach higher levels of education and literacy, enjoy better employment opportunities, and have access to family planning. So how can we lower birth rates effectively? With win-win policies, which are policies that benefit both the economy and an environment through voluntary moderation of population growth, such as family planning, access to reproductive health, and education of women. So what if we do not adjust? Urban areas where population growth is most rapid due to a combination of natural increase and migration often experience major social and infrastructural problems. For instance, urban populations in Asia and Africa are projected to double over the next 30 years, leading to inadequate housing and sanitation, congestion, air and water pollution, deforestation, and solid waste problems, and soil contamination. If population growth continues unchecked, the world could face significant environmental and economic consequences. The global population is projected to reach nearly 10 billion by 2050, potentially causing a 50% rise in carbon emissions, worsening climate change. The UN estimates the world will need 70% more food by 2050, increasing the strain on natural resources like water and land. The WWF reports that human activity has already caused a 60% decline in wildlife population since 1970, and unchecked growth will accelerate biodiversity loss. Economic costs of environmental damage could result in a 2 to 4% loss in global GDP by 2100, with developing nations suffering the most. Rapid urbanization could increase slum populations to 1.6 billion by 2030, leading to overcrowding, poor sanitation, and health crises. Addressing population growth and improving family planning could alleviate many of these challenges and support a much more sustainable future.